Okay, number 32. We are told that air breaks down and conducts charge as a spark. It breaks down and conducts charge as a spark if the electric field magnitude exceeds 3 times 10 to the 6 volts per meter. Determine the maximum charge that can be stored on an air-filled parallel plate capacitor with plate area of 2 times 10 to the negative 4 meters squared. And then finally find the voltage, the electric potential difference for 75. This is actually supposed to be 75 microfarads. Okay, with the stored charge. So, this is going to be... Okay, so we have some identities in the book that we can use, which is really what a lot of this comes down to. Capacitance is equal to epsilon naught times A over delta X, which is a distance, right? So capacitance is also equal to charge over the electric potential difference. Okay? Where the electric potential difference is equal to negative electric field times the change in the distance. So now we have capacitance is equal to charge over negative E times the distance. Right? Great. So let's set these up. So we actually have, we can take this and plug this into Q is equal to delta V times C. Right? That's also equal to C times negative E times the change in the distance. That's also equal to what we have up here, epsilon naught times area times the change in the distance. So that's capacitance, right? I just plugged this in for C. Then I'm going to leave this here. E, we'll do it like this, E times the change in the distance. Well, so this is what the charge is. We're looking for the Q max, right? We're given all these values that we can plug in, so this is going to end up being Q max here. Now, notice that this delta X cancels, and it leaves us with epsilon naught times the area times the negative of the E field. Okay? So we can plug all that in. We're given a bunch of stuff, 8.85 times 10 to the negative 12. Coulombs squared, newtons times meters squared. I don't remember exactly. 2 times 10 to the negative 4 meters squared. Oh. Let's move this over here because I'm running out of room. Okay, so now we have times 3 times 10 to the 6. It was volts per meter, and that's actually the same as newtons per coulomb, which is going to be a more useful unit. It's the same thing. You can look it up. It works out. Okay, so now we plug all this in, and we end up with a value of about 5.31 nanocoulombs. That's Q max. Okay? So just notice what I did here. I really just pulled a couple of formulas straight out of the summary of the book. Capacitance is equal to epsilon naught times area over distance. Capacitance is equal to Q over delta V. We can plug this in. We're given an electric field, so that's why this worked out so well. Plug that in, set them equal to each other, and just do a little bit of canceling, and then you're able to plug it all in and get a value. So that's not too bad. Next, we want to find the electric potential difference for 75 microfarad capacitance. Okay, so we're given, and we want to use Q max, so we're given Q max, right? We know that. We found it out. So we're given a capacitance. We know Q max. Now we can just plug this in and find the electric potential difference. Times 10 to the negative 9 coulombs, right? I plug this in here over the capacitance that we're given, 75 times 10 to the negative 6 farads. And that's going to equal about 0.71 coulombs over farads, which is the same as saying volts. So that's the potential difference. Okay? Great. Moving on to the next problem. We're given an air-filled capacitor. We're told the area of the plates are these values here. It's written down in the book. The distance between them is this value here. So we have an air-filled capacitor. This is the distance, right? The distance between the plates. This is the area of the plate, of each plate. Something like this, right? And we're told that there's a voltage difference of, an electric potential difference of 20 volts. We want to find the electric field between the plates. Okay, well, we have a formula that we can work with pretty easily. We know what D is, we know what the distance is, we know what the potential difference is, we want to find E. So we just rearrange. Delta V over delta X negative. And that's equal to 20 volts over 1.8 times 10 to the negative 3 meters. Which gives us a value of about 1.1 times 10 to the 4 volts per meter, which is an electric field units. And it's moving toward the negative plate. Which, I mean, that's, because that would have been a negative value. What I didn't do was keep the negative here. That's why I just said it's moving towards the negative plate. That's why we have this negative value. So what that means is these are positively charged, this plate over here, and this plate over here is negatively charged. So the E field is going to be pointing this direction. That's what that means. Okay, next is find the capacitance of the capacitor. Okay, well, we know some formulas for capacitance. We have an area, we have a distance, we know epsilon naught. We can just plug these values in. 8.85 times 10 to the negative 12. Coulombs, newtons, meters squared, 7.6. We were given this value in centimeters. We can go 0.01 squared meter squared over 1.8 times 10 to the negative 3 meters, because this was the distance, right? This is going to give us a value of 3.74 times 10 to the negative 12 farads, or we can say 3.74 picofarads. Pico is a unit of negative 12, right? Next, we are asked to find the charge on each plate. So, to find the charge on each plate, recall that we know the potential difference, we know the capacitance, we just found that, so we just plug these things in. 20 volts times 3.74 picofarads, which gives us a value of 7.48 times 10 to the negative 11 farads. So just be careful when you're plugging these back in. Picofarads is 10 to the negative 12, right? So you want to watch out for that.